We want to impose our boundary conditions on this solution. So let's impose the boundary condition at the left end first. So at the left end, the temperature is set to 0 at x equal to 0, and that tells us that a is equal to 0. So we're just going to get rid of this whole first term, leaving us with x of x is equal to b sine of kx. So far, everything is the same as we had done before. Now let's see what happens when we impose our other boundary condition. So if we impose our other boundary condition at x is equal to L, we first have to take the derivative of u with respect to x, and then plug in x equal to L. So let's do those separately. The derivative of u with respect to x is kb cosine of kx. And then we impose x equal to L there. That tells us that kb times cosine of kl must be equal to 0. Well, one solution of this could be that b is equal to 0, but of course we don't want that solution. That tells us that we have no solution for x of x. So instead we're going to choose the possibility that k times L is equal to n pi over 2, where n is some kind of odd integer. That would ensure that cosine is always 0, and so that would ensure that we can always solve this boundary condition. Okay, as before, we have figured out a value of k, the separation constant, that will allow us to solve our boundary condition, but we haven't figured out what b is, that arbitrary constant b, and that's similar to what we had done before. We didn't have a solution for that. So we figured out a solution for capital X of x, including the value of the separation constant. All we need to do now is find a solution for t of t. So what we need to do is we need to take our t differential equation, t dot over t is equal to minus alpha times k squared, and solve that ordinary differential equation for capital T.